Good morning, good afternoon, good evening, everyone. Today we want to study entity relationship model or ER model for databases. Databases are everywhere, from applications on your phone to massive enterprise systems. Today, we will focus on designing these databases using ER models. This ER model is a method that helps us plan before we build, and it is used to ensure our databases are efficient and reliable. Let's see why this matters. So far, we have assumed a given database schema and studied how queries are expressed in formal language. In this lecture, we focus on Entity Relational Data Model or ERM. This ERM provides a means of identifying entities to be represented in databases and also help us to see how these entities are related to each other. We will see how an ER model can be transformed into a set of relation schemas and how some of the constraints can be captured in that design. So we will go for design process, modeling, constraints, ER diagrams, design issues, weak entity sets, extended ER features, design of the bank databases, reduction of relation schema, database design, and UML. Let's get started. So the main question is, why bother with database design? A well-designed database saves times, reduces errors, and supports growth. Poor design leads to slow performance, duplicate data, or even system crashes. Think of it as the foundation of a house. Get it right, and everything else falls into place. Our goals are simple: ensure data integrity, minimize redundancy, and optimize retrieval speed. We want a system that's easy to maintain and scale with user needs. These ERM help us achieve this by giving us a clear blueprint to follow. This schema diagram that you can see here is a university database with tables like student, department, advisor, instructor, course, prerequisite, text, time slot, teach, section, and classroom. Our examples are from this database. Now we are at the stage of designing a database. Database design is in two phases. Phase 1 user requirements and phase 2 data model selection and requirement translation into conceptual schema. In fact, the task of creating a database application is complicated. We need to design a database schema, design the program that access and update the data, and also we need to design a security schema to control access to data. So in these phases, the phase 1 involves gathering user requirements, what data is needed, and how it will be used. Phase 2 translate these requirements into a conceptual schema using a data model like ER model. These two phases ensure the database align with user needs. Design phase include logical design and physical design. In the logical design, we define the schema and relations, a blend of business and technical decisions. And in physical design, we deal with storage efficiency, indexing, and performance optimization. Both logical design and physical design are essential for robust databases. In logical design, we decide on the database schema. For example, we want to find a good collection of relation schemas. Then we have two decisions, business decision and computer science decision. In the business decision, we think of what attributes should we record in the database, While in the computer science decision, we think of what relation schemas should we have and how should the attributes be distributed among the various relation schemas. And in the physical design, we try to decide on the physical layout of the database. Now, let's talk about the ER model, or we can say entity relationship model. This is a kind of conceptual tool we use to design databases visually before we go for implementation phase. This ER model helps us to map out the things, or you can say the entities or objects, and also their properties, and you can say how they connect to each other through relationships. And this ER model is like a sketch that bridges the gap between real-world concepts and the technical structure of a database. It is simple but powerful, and it is what we will focus on next. The ER model is developed to facilitate database design by allowing specification on enterprise schema that represent the overall logical structure of a database. And also, it is very useful in mapping the meaning and interactions of real-world enterprise onto a conceptual schema. Because of this usefulness, many database design tools draw on concepts from the ER model. So the ER model's core components are entity set, relationship set, and attributes. The entity set is collection of similar entities. The relationship set is connection between entities, and attributes are properties of entities. These form the building blocks of database schema. So first up in the ER models are entities. An entity is a distinct object like for example, you can say person, company, event, plan, or in our schema, like instructor. For example, in a university database, entities are student, course, professors. Then we have entity set. This is a group of similar entities like all instructors, or you can say set of all persons, all companies, all trees, all holidays. In our database, for example, we can say instructor set include attributes like ID, name, street, city, salary, while course ID, title, and credits. Then we may have a subset of attributes. So each entity represents a table in the final database, and we depict them as a rectangle in ER diagram. Entities are the building blocks, so identifying them correctly is the first step to a solid design. Here we see two concrete examples of entity sets. Entity set instructor is and student relation is here. You can see the first column here is ID and the second column is name, right? The instructor table lists faculty members with IDs and names, while the student table does the same for student ID and student name. Notice how each row represents a unique entity. So these are entities in our table. Then we have relationship set. A relationship associates entities like a student advised by an instructor. Then a relationship set formalizes these associations. For example, the advisor set pairs student IDs with instructor IDs, right? So for example, here we have student entity here, we have instructor entity here, and the relationship is advisor. It means this student with this ID here is under supervision of this professor. So we show this way. We can show mathematically then, for example, in this way E1, E2 in such a way that E1 is in 1, E2 is in E2 up to En in En. And then we can represent the relationship set. Here, the advisor relationship set links instructors to student. Each entry, like for example, this 44553, is under supervision of this professor. So it means this is a relationship. Such relationships are central to modeling real world interactions. Relationships can have attributes. For example, an advisor relationship might include a date attribute to track when advising begins. These attributes add context to the connection between entities. For example, this student was under supervision of this professor on this date. The same thing, this student was under supervision of this professor on this date, right? So, an attribute can also be associated with a relationship set. And in here, the advisor relationship set between entity set instructor and students may have the attribute like date here. Then relationships vary in terms of degree. A binary relationship involves two entities. Then we can say like a student and project guided by a professor. Then we may have higher degree relationships like ternary, etc. These are less common but equally important. So when we say binary relationship, it means involve two entity sets, or you can say degree of two. For example, a student work on research project under guidance of a professor, right? So relationship project guide is a ternary relationship between instructor, student, and project. Cardinality constraints define how entities relate. These cardinality constraints express the number of entities to which another entity can be associated with a relationship set. For a binary relationship set, the mapping cardinality must be one to one to many to one, and many to many. So here we can see different cardinality types. You can see here one to one, it means one instructor, one student, one instructor, one student, one instructor. And also we may have professor who has no student under supervision. This is one to many that you can see one professor to a student, one professor to a student, and one professor, one student. So some elements in A, for example, may not be mapped to any element in another cell. Understanding this is key to accurate modeling. Here we can see many to one and many to many. Again, what we see here, so many maybe professors teach one course. You can see here one to one, many to one. Again, you can see many to many. It means this with both of two and this with both of two, right? Still, we have some elements in B that are not associated or mapped to any element in A. Attributes can be simple, like atomic, like for example, age. They can be composite, like nested. For example, you can say address. They can be single valued. They have a single value. They have, for example, a name, right? Or they can be multi-valued, like multiple phone numbers, right? And they may be derived. For example, we calculate age based on birth date, right? Each type serves a specific purpose in design. So for example, here we have a composite attribute, right? Name is composite, but we made it first name, middle name, and last name. Address is a composite, but it can be go to a street. A street is still composite, like a street number, a street name, but city is single, right? So simple, right? Postal code is simple. So in here, we should care of domain, and domain is the set of permitted values for each attribute. Redundancy is a very important to be take care of it in database design. Redundancy, like department name appearing in both instructor and department table. So we have to go for proper normalization to eliminate redundancy by separating data into logical tables. Then we have entity sets. Entities can be represented graphically like entity set using rectangles, attribute listed inside entity rectangles, and primary key underline. So you can see here this is an entity set, right? And these are attributes, and this underscore it means primary key. ER diagrams use rectangles for entity sets like instructor here and student here. These diamonds are used for relationship. So, and then here we can have attributes. Then we can go for primary key use underline these clarifying unique attributes. So in here we can see ER diagram corresponding to instructors and students where they are in relation using the advisor attribute. Here the advisor relationship include a date. So as I told you, the student was under supervision of a professor in a specific date. This adds detail showing when the advising relationship began, which might be useful for tracking duration or performance. So in here, this is a diagram with an attribute advisor, and this has an attribute. Entity set of a relation needs to be distinct. In every relationship, each occurrence plays a role. For example, in here we can see that course ID, and prerequisite ID in the relationship of course and prerequisite. Prerequisite means when you want to take a course, you must already pass another course. For example, if you want to go for advanced programming, so if this course is advanced programming, you must already pass algorithms, right? So algorithm is a prerequisite for advanced programming. Rules clarify how entities interact with a relationship. Here we can see cardinality in action. In mathematics, the cardinality is simply the number of something. In the context of relationships, we want to see the number of connection between two or more relations. So we may show one by this arrow and many with a line, right? So just be drawing either a directed line or undirected line. For example, here we can see one-to-one relationship between instructor and student. It means a student is associated with at most one instructor via relationship of advisor. So this one, it means at most one, at most one. Here we can see an example of one-to-many relationship, right? So this is for many and this is for one, right? So one-to-many relationship between instructor and student. And instructor is associated with several. It can be 0, 1, 2, up to many, right? You can say n, right? So we can say an instructor is associated with several students like 0 to n students via advisor. But a student is associated with at most one, right? You can say at most one. It means one student cannot have two professors as advisor, not teaching. So we can see the difference between lines that you can see arrow, directed or undirected. Here we can see many, this is many to one relationship. This is many to one relationship between instructor and student. And instructor is associated with at most one student via advisor, and a student is associated with several including 0. So you can say 0, 1, 2, up to many via advisor. Here we can see an instructor is associated with several including 0 student, and also a student is associated with several, possibly 0 instructor via advisor. So here we can see total participation and partial participation. The total participation means every entity must join a relationship. Must join. It means you can say all students must be advised. On the other hand, for the case of partial, it allows optional involvement. For example, not all instructor must have a student to advise. We show the total participation by a double line, as you can see here, and partial with a single line. So again, every entity in the entity set participate in at least one relationship in the relationship set. Participation of a student in advisor relation is total participation. It means every student must have an associated instructor. But in case of partial participation, some entities may not participate in any relationship in the relationship set. For example, participation of instructor in advisor is partial. They may have a student to advise or they may not have. It's okay. Sometimes we have more complex constraints. We see how to show more complex constraints in here. Like you can see here, L to H, where L is the minimum, like L is equal to 1 total participation, and H is the maximum cardinality. For example, when we say H is equal to 1, the entity participates in at most one relationship. And when we say H is equal to a star, it means no limit here. You can see here, instructor can advise 0 or more students, right? So you can see here, we can say 0, 1, 2, up to many. And here you can see 1 and 1. It means a student must have one advisor and only one advisor, cannot have multiple advisors. Attributes can be hierarchical. Here, name is composite, like first name, middle name, last name. Address is nested, street number, street name, apartment name, city, state, zip, right? Phone number is multivariate. And this age can be derived from date of birth. So this table shows a ER diagram with composite, multi-valued, and derived attributes. Then we have weak entity. A weak entity lacks a unique key and depends on a strong entity. For example, a section is a weak entity because it relies on course, and course is a strong entity because for the identification of a section there must be a course. Weak entities are shown with double lines. So we can see we show by double line, and you can see entities we can show by dashed line. You can see here we show by dashed line. Weak entity is an entity that cannot be uniquely identified by its attributes alone. It must use a foreign key in conjunction with its attribute to create a primary key. The foreign key is typically a primary key of an entity it is related to. Like this underline the discriminator of weak entity set to identify a strong entity set is depicted by a double line diamond here. And primary key for section, like section ID, semester, and year, these are the primary key for section. This is the ER diagram, integrates all concepts like entities, for example, student, department, instructor. Then we have relationships like student, department, advisor, ins department. These are the relationships, attributes, and constraints. This is our university enterprise diagram. So as I said, we have like relationships, and also you can see we have keys, IDs, department name. So this is like course ID here. So this diagram models the relationship between departments, instructors, and students, courses, sections, classroom, and time slide in a university setting by capturing how they interact for scheduling, advising, and academic tracking. Entity sets and relationship sets can be expressed uniformly as a relation schema that represent the concept of the database. A database that conforms to an ER diagram can be represented by a collection of schemas. For each entity set and relationship set, there is a unique schema that is assigned the name of the corresponding entity set or relationship set. So each schema has a number of columns generally corresponding to attributes which have unique names. So a strong entity set reduces to a schema with the same attributes like student, ID, name, and total credit. And a weak entity set becomes a table that includes a column, right? You can see here. So here we can see a schema for relationship set advisor. We can see here instructor and student. This is a kind of many-to-many relationship set is represented as schema with attributes for primary keys of two participating entity set and any descriptive attributes of the relationship set. You can see here we have advisor, SID, IID, right? SID it means student ID and IID it means instructor ID. Then composite attributes are flattened out by creating a separate attribute for each component attribute. So given entity set instructor with composite attributes like name with component attributes like first name, mid name, last name, the schema corresponding to the entity set has two attributes like name, first name. Ternary relationship involve three entities like project guide linking students and professors and also project. So we have three here. These are rare but model complex interactions. More relationship sets are normally binary. There are occasions when it is more convenient to represent relationships as non-binary. So here we can see ER diagram with ternary relationship, student, instructor, and project. These symbols standardize ER diagram. So rectangles are used for entities, diamonds are used for relationship set. These double diamonds identify relationships for weak entity sets. Then diamond attached to E with double line, it is total participation. And these undirected lines of diamond is for many to many relationship. This directed line is one to one relationship. This is for many to one. This is for rule indicator. This is for primary key. These are for attributes, discriminating attributes of weak entity set. And this is for cardinality, one to one, one to many. And the last topic is UML, Unified Modeling Language. UML is a broader modeling language. Its class diagram resemble ER diagram, but they include methods and visibility like public and private. Both tools are vital for system design. We already studied ER diagram to model the data representation components of a software system. But data representation forms only one part of an overall system design. Other components include models of user interaction with the system, a specification of functional modules of the system and their interaction, etc. UML is a standard developed under the OMG Object Management Group for creating specifications of various components of a software system. UML has many components to graphically model different aspects of an entire software system. So we have class diagrams. These correspond to ER diagrams, but several differences. Then we have use case diagram. They show the interaction between users and the system. Then we have activity diagram. They depict the flow of tasks between different components. And then we have implementation diagram. They show the system components and their interaction. So here we can see the difference between ER and UML. While ER focuses on data, UML class diagrams add behavioral details. For example, UML includes methods for public and private and generalization like inheritance. So here is the difference between ER and UML symbols. In here, an entity, for example, like E, is represented as a rectangle with attributes like A1, M1, but in UML, the same entity is shown as a class, like rectangle with attributes listed inside, prefixed by visibility indicators like A1, private, and plus M1, it means public. UML uses plus for public and minus for private, and also they use hash symbol for protected attributes. Then for binary relationship, you can say a binary relationship R between entities E1 and E2 is depicted as a diamond with rules like rule 1 and rule 2 labeling the connections. But in here, in UML, the relationship R, you can see here, is shown as a line between classes E1 and E2 with rules rule 1 and rule 2 at the ends of each line. Then we have here a relationship with attributes. In ER, a relationship R between E1 and E2 can have its own attribute like A1 attached to the diamond. But in here, we show different. In UML, this represented as an associated class like R. This is a class connected to the relationship line via a dashed line connecting the attribute A1. Then in case of the cardinality constraints, this here we have like 0 to many or 0 to 1, right? This indicating how many instances of one entity can relate to the another. But in UML, cardinality is similarly shown on the associated line here, as you can see, with the same like ER. Then here we can see an array relationship. This is an array relationship like R involving three entities E1, E2, and E3. And we show the diamond connected all together, indicating a relationship among them. This is called as ternary relationship. And the same thing in here, the same n array relationship R is represented as a diamond shape association with E1, E2, and E3. In here also for overlapping generalization, here generalization is depicted with a triangle connecting a parent entity like E1 to child E2 and E3. The overlapping label is indicating that the instance of E1 can belong to both E2 and E3. For example, a person can be both a student and an employee. And for the case of UML, generalization is shown with the solid line and an empty triangle indicating, and so you can see here, this pointing E2 to and E3 to E1. The overlapping label indicates that the subclasses can overlap, meaning an instance of E1 can be an instance of both E2 and E3. Then here we have disjoint generalization. So this is similar to overlapping but labeled with disjoint, meaning an instance of E1 can belong to E2 and E3. For example, a vehicle can be either a car or trunk, but not both of them. And in the case of UML, we represent the same way as overlapping generalization in UML, like solid line with a triangle, but labeled with disjoint here, indicating that the subclass E2 and E3 are mutually exclusive. Okay, to sum up, database design and entity relationship model, ER models, are all about turning real-world needs into structured and efficient systems. In this lecture, we have covered the basics, entities, attributes, relationships, and how to visualize them with ER diagrams. With these tools, you can build databases that are robust and scalable. Thank you for listening. I'd love to hear your questions or thoughts by leaving a comment below this video lecture. Thank you and see you in the next lecture.